Assalamualaikum to Dr. Fairuz. I am Anis and this is Group 70 presentation for distillation column design case study. Next slide. A distillation column is mainly used in the oil and gas industry. It separates liquid mixture into respective component or fraction. Feed will enter at central column, liquid will be heated at bottom and partial vaporization occur. Heavy component with low volatility will exit as bottom product, while light component with high volatility becomes vapor, exit at top and condense back into liquid to exit as distillate or to be recycled. Next slide. Generally, distillation column contain the listed component. Below are the distillation column design condition. Next, I will pass to Farhan.
Okay, for design procedure, we start off with material balance where we need to find the amount of distillate and bottoms, which the molar flow rate for feed, distillate, and bottoms is as shown in this table. Next, for column height, it can be obtained through McCabe-2 method where R equals to 1.3 R min and also the efficiency is 85%. So we obtain the number of actual stages to be 20 stages. From there, we can determine the height tray by assuming the plate spacing and also safety factor. With additional top of 4 feet and also bottom of 10 feet, the column height is 15.27 meters. For column diameter, it is typically depending on design velocity, which is typically 80 to 85% of flooding velocity, where K1 is obtained from this graph, and design velocity for top and bottom is as shown. From there, we obtain the downcomer area, and finally, the column diameter can be obtained. From there, we obtain the column diameter for bottoms because it has a higher value, and with the increment of 0.1 meters, the column diameter is 1.3 meters. Next, for plate design, several assumptions are made with the liquid flow arrangement to be cross flow. From the table, it is shown for the assumption and a formula for provisional plate design. Next, for whipping. For whipping point, we have to calculate for K2, which can be obtained from this graph with versus wear height, which the wear height calculation can be obtained from the left. Then we have to compare that with actual minimum vapor velocity and ensure that it is higher than whipping point. For our design, it is said that whipping does not occur. For plate pressure drop, it can be divided into dry plate drop, residual loss, and also head of clear liquid. And it is obtained to be 113.47 millimeters of liquid. Next, I will pass to Erin for the next part.
Thank you. Next, in designing the downcomer backup can be calculated by the sum of downcomer head loss, head of clear liquid, and plate pressure drop. The downcomer head loss can be calculated via this formula, where a bigger value between the downcomer area and the clearance under the downcomer is selected to be substituted as AN. So in this case, we have selected AD. The design, however, must satisfy these conditions, where the downcomer backup should be less than the froth height and the residence time should be at least 3 seconds or more. Next. So in this case, by substituting our values in the formula, the downcomer backup and residence time satisfy the values, making this design acceptable. Next. For designing the perforated plate, the ratio between the weir length and column diameter is determined to get the angle theta C using this figure below, where we can determine the angle theta by subtracting theta C from 180 degrees. Next. Then by calculating the area of unperforated strip and the area of coming zone using these formulas, the total perforated area can be calculated by subtracting these two areas from the active area to get 0.82 meters. Next. To check that the design is acceptable, the ratio between pitch length and hole diameter should be within this range. Next. So by substituting the hole and pitch area values and finding the intersection in the figure on the right, the design is acceptable due to the ratio is being in between range. Next. The number of holes in the plate can be determined by dividing the total hole area by the area of one hole to get a total of 5,138 holes. Next. And in checking the entrainment, the intersection between the flooding percentage and the liquid vapor factor is the intersection is found in figure 11.29 to find the fractional entrainment. And as long as this value is less than the maximum value of 0.1, the design is acceptable. Next. So in total, our process design can be summarized in this table. Passing on the next section to Ricky.
And I will continue with the utility requirement. Cooling water is chosen as the cooling utility because the temperature range is between 40 to 120 Celsius. Hence, it can be used to condense vapor in the condenser. The temperature of cooling water is assumed at 55 Celsius. The volumetric flow rate of cooling water needed is around 36 meter cube per hour. NP steam is chosen as the heating utility. The pressure of NP steam is assumed to be 7 bar, and the volumetric flow rate of steam obtained is around 1.4 meter cube per hour. Next. For safety consideration, both benzene and taurine are flammable. Their liquid and vapor are highly flammable. Fresh bread from a far distance to leakage can occur if mixed with ignition sources. Moreover, benzene can ignite at room temperature and emit vapor which form explosive with air. The measure and precaution need to be taken while handling both benzene and taurine is store away from ignition sources, take preventive measure against static discharge, and use non-sparking ventilation system and approved explosive-proof equipment. Besides that, both benzene and taurine are very toxic. They can cause severe eyes and skin irritation if in contact and may be fatal if swallowed. Furthermore, long-term or repeated exposure to benzene can cause damage to blood and immune system and may cause cancer. The preventive measures that can be taken are using backup controls such as double seal implant to avoid emission during failure, stored in a well-ventilated places, and appropriate PPE need to be worn. Next, I will pass to Yihao to explain about mechanical design.
Thank you, Ricky. I'm Yihao. Now I'm going to present the mechanical design part. The distribution column can be classified into batch column and continuous column. In batch column, the operation mode is charged with a batch raw material for distillation process, while for continuous column, the operation mode is fed with the continuous stream, and it can be further classified into tray column and pack column. Next slide. To calculate the design temperature, the highest mean metal temperature expected in operation is 114.42 degrees Celsius, and including the transition condition, which is 10 degrees Celsius, the design temperature is calculated as 124.42 degrees Celsius, while for design pressure of distillation column, it takes as 10% above the operating gauge pressure, which is 1.11 bar. For material constructions, the choice of material is depending on the construction of unit operation is to ensure the operation maintained at its highest efficiency. And the guideline of choosing the material are depending on cost, corrosion resistance, maximum operating temperature, and etc. In short, carbon steel is suitable to be selected as the material construction of the distillation column. Next slide. For selection and calculation of head enclosure, there are a few types of head enclosure designs such as flank heads, hemispherical heads, ellipsoidal head, and tori spherical heads. And based on the table, the tori spherical head is selected in this study, and the calculation of the minimum thickness of the head is determined by using the equation on the slide below. Next slide. For the vessel support, there are three types of vessel support. For example, saddle support, skirt support, and bracket support. In this study, the skirt support is selected as the vessel support for the distillation column because of the skirt support is suitable for the vessel which are land in vertical position. The skirt support is suitable for tall vertical vessel as it has good resistance to bending subjected to the wind directions. Next slide. There are three common arrangements of the way. Next slide. Is welded and to the bottom heads. So the most preferred arrangement are the second one, B. So next slide is showing the summary value of the mechanical designs. Now I would like to invite Anis to continue the presentation.
Thank you, Yihao. Next slide. In calculation of bare cost estimation, important values and parameters are listed. Next slide. Firstly, tower purchase cost is calculated using equation for Appendix A, analysis, synthesis, and design of chemical process. The constant K1, K2, and K3 is obtained from table A1. Capacity of tower is calculated, values are plugged in, and purchase cost tower is $80,480. Next slide. Bare module cost of tower is calculated. Value of B1, B2, material factor, and identification number is obtained from table A3, A4, and figure A18. Pressure factor is then calculated using the shown equation. Thus, bare module cost of tower is $79,473. Next slide. Calculation for tray purchase cost is similar to tower purchase cost with different value of constant and capacity equation. Tray purchase cost is $1,136. Next slide. Bare module cost of tray is calculated using formula from table A5. For number of stage more or equal to 20, quantity factor is 1. Bare module factor is an identification number is obtained from table A6 and figure A19. Thus, bare module cost of tray is $22,735. Next slide. Calculation was made with values of year 2001. CHAPTER is used to estimated price in 2021. The currency is changed to Malaysian ringgit. Total bare module cost is 791,674 ringgit. Next slide. Case design conclusion. Firstly, process design, hydraulic design, and mechanical design consideration may improve the efficiency of equipment. Second, cost estimation and safety aspect consideration will ensure an equipment feasibility. Lastly, several aspects can affect distillation column. Thank you.